20 ohm, a voltage source of 25 volt, and this is a current source 3 amps. This is a 4 amps, 4 ohms, okay, and these are the two terminals labeled as an A and B. We can say it is an open. So in order to find the Thevenin's equivalent circuit for the circuit shown in figure 1, calculate the open circuit voltage VAB. So this is an open circuit voltage because these two terminals we kept it as an open, and these two terminals we labeled as an A and B. Note that when the terminals A and B are open, there is no current flowing through this particular 4 ohm resistance. If this is open, obviously there won't be any current across or through this particular branch. So that is 4 ohm resistor. Therefore, the voltage VAB is same as voltage across 3 amp current source. It means the voltage across terminals A and B is nothing but the voltage across these 2 points. In the sense, across this particular 3 amp current source, labeled as an V1. To find the voltage V1, solve the equation for the singular node voltage by choosing the bottom right node as a reference. So the same way we did it already. So this comes like how much? If you see this, if you see this V1 should be equal to what? 25 minus 5. V1 should be equal to what? I should be equal to what? V1 minus 25 divided by 5. So this is nothing but V1 minus this voltage. We say this is in V. So V1 minus V divided by R1. Okay? Plus V1 divided by, what is this? R2. Plus, what is that? Already, as we said that the node voltage we need not to assign if the value is given. So was plus, what is that? 3. So how the expression comes like V1 minus 25 by 5 plus V1 by 20 minus, what is the current value? Minus 3 should be equal to 0. The summation of all the voltage should be equal to 0. So if you see this equation, you'll get it the same one. What I was saying, V1 minus 25 by 5 plus V1 by 20 minus 3 should be equal to 0. And if you solve this equation, you will get V1 as an 32 voltage. 32 volts. What is the next step? The next step is to short circuit the terminals and find the short circuit current for the circuit shown in figure B. Note that the current is in the same direction as falling voltage at the terminals. So now what we did is, we have short circuit the current. Here you can see that short circuit current. We have shorted this particular terminal A and B. So we can say that the current through this particular terminal now is considered as an ISC, nothing but a short circuit current. So current ISC can be found if V2 is found. Now if we have the value of V2, we can clearly say that V is equal to ISC is equal to V2 by R. So what we need to do, by using the bottom right node as a reference node, the equation for V2 becomes, so please look here, let's go through this. It will become like, this is V2, right? So the expressions comes like V2 minus 25 by 5 plus, okay, V2 minus 25 by 5 plus V2 by 20 minus, this is 3 they have given, minus 3, okay, minus 3 plus V2 by, this is 4. So how the expression comes like V2 minus 25 by 5, V2 plus 20, this is a minus 3 amps, plus V2 by 4. So summation of all those voltage should be equal to 0. Now please look here. The same one, V2 minus 25 by 5 plus V2 by 20 minus 3 plus V2 by 4 is equal to 0. So if you solve this, you'll get V2 as an 16 voltage. Okay, so what is the short circuit voltage, short circuit current now? From here, ISC will be equal to what? V2 by 4. So it comes like 16, we got it V2 as in 16 volt. So 16 by 4 is nothing but 4 volt. So this is ISC is equal to 4 amps. So what is Thevenin's resistance? ZTH should be equal to VTH, the total voltage by the total current. So this is 32. You can see here, this is 32 divided by 4. You got it as an 8 amp. And this is nothing but Thevenin's equivalent circuit. So this is how we can find it out, applying superposition theorem to a linear network. Now the next is called as an Norton's theorem. So Norton theorem for a linear electrical networks states that any collection of voltage sources, current sources and resistors with two terminals is electrically equal to an ideal current source I in parallel with single resistor. So it is just as simple as the Thevenin's equivalent circuit. In the case of Thevenin's theorem, we said that any linear network can be replaced by an equivalent voltage source in series with a current source. So whereas in the Norton, any linear network can be replaced by an equivalent circuit consists of a current in parallel with resistance. So there in the case of Thevenin's, we have taken as an ETH in resistance in series with a ZTH. Whereas in the case of Norton's theorem, any linear network can be replaced with a single current source in parallel with a single resistor. So as that was defined as an ETH and ZTH, here we will be saying this is an IN and RNO or RN. Okay, so this is how the equivalent Norton network for any linear network circuit. So to calculate the IN and RN, remove that portion of the network across which the Norton equivalent circuit is found. Mark the terminals of the remaining two terminal network. Okay, and to find out RN, calculate RN by first setting all sources to 0 and then finding the resultant resistance between the two marked terminals. So this is one. And IN, how to calculate IN in the circuit? First, returning all the sources to the original position, because earlier we have made it to short circuit. So returning all sources to the original position and then finding the circuit, the short circuit current between the marked terminals. It is the same current that would be measured by an ammeter placed between the marked terminals. So what is the conclusion? Draw the Norton equivalent circuit with the portion of the circuit previously removed, replaced between the terminals of the equivalent circuit. Now we will very elaborately see what is the statement and how we can prove the Norton's theorem. So there is a difference between the Thevenin's theorem and the Norton's theorem. Thevenin's theorem reduces a two-terminal active network of a linear impedance and a source to equivalent voltage source and series impedance, whereas Norton's theorem replaces the network by an equivalent constant current source. So how the statement can be given? Any two-terminal linear network containing sources and impedances can be replaced by a constant current source in parallel with a single impedance. Okay, the current is the short-circuited current between the two terminals of the network, while the impedance between the two terminals is the impedance when all sources of EMF are replaced by its internal impedances. So these are the two conditions how we can find out the Rn value as well as or Zn value as well as In value. So equivalent In and equivalent Zn, with these two conditions we can find it out. Now just see into this particular figure 17, and this is labeled as an A circuit, this is B and this is C. So this is the main linear network circuit where which we are finding out the current through the load resistance ZL. And now this can be replaced in this manner, keeping this two particular, making this two terminals in short circuit for once, and the second time making these two terminals as an open when the source is removed into this. So this is labeled as in circuit A, this is B and C. Okay. So first of all, this point A and B are short circuited. So you can see, follow up this particular circuit B now. So this terminals A and B are short circuited in the sense there is no load resistance in the circuit. Okay. So this, if you short circuit this, obviously we have removed this ZL and this Z2 is ineffective. Because we have made short to these two terminals, it means this Z2 is ineffective and ZL is no more into the circuit. So what would be the current in the circuit now? Current is nothing but V by R. So current in the circuit will be, I should be equal to E by R plus Z1 because these two resistors are in series with each other. So you can say that this is an IN value. How to find out the IN value? This is how the terminals A and B should be made as in short. So IN will be equal to E by R plus Z1. So now you can see that IN is equal to E plus R plus Z1. Now next is what? Next we need to find out Zn or Rn, isn't it? So to find out the value of Zn and or R1, battery should be removed. This battery should be removed. So follow up this particular place, figure C. Here we have removed the circuit battery. Okay. Then we made these two terminals as an open. So making these two terminals A and B open and removing this battery E, we can find out the total resistance or impedance in this particular circuit. So this is how it looks like. But according to the terminals A and B, these two resistance R and Z1 are in series and equivalent of this two resistance is in parallel with the other resistance or impedance called Z2. Isn't it? So if you solve that, so this comes like, this is Zn, right? So 1 by Zn should be equal to 1 by R plus Z1 plus 1 by Z2. And mathematically, if you solve it, Zn will come as R plus Z1 into Z2 divided by okay. So here there is a small mistake. Zn should be equal to R plus Z1. Zn should be equal to R plus Z1 into Z2 divided by, it should come like R plus Z1 plus Z2. So the plus sign is missing here. Okay. So this is how we can find out the value of IN and Zn. Now this have come into an equivalent circuit of Norton, like single current source in parallel with a single resistor. So this is an IN. So I was equal to what? E by R plus Z1 and Zn was equal to R plus Z1 into Z2 into ZL divided by into Z2 divided by R plus Z1 plus Z2. So this can be called as an equivalent Norton circuit. Now we need to prove it. So how we can make it that? So the Norton equivalent circuit may be found from Thevenin's equivalent. So what we did is we have converted that particular linear network, this figure A, into a Thevenin's equivalent. So can we draw in this? Because any linear network can be replaced with a single voltage source in series with a single resistor. So we have converted that linear network into a Thevenin's equivalent circuit as shown in figure A. So this is how ETH, this is ZTH, these are the two terminals A and B, and this is Z. Okay, now we will show that this is I is the current flowing through this particular ZL. So this I should be equal to this I which is flowing in this particular ZL. Because now that the same linear network is converted into Thevenin's equivalent in figure A, and same linear network is converted into a Norton's equivalent, which is shown in this particular 19th figure B. So this is a single source. So I will be equal to what? We have converted this into this. This particular diagram, circuit diagram, is converted into a Norton's equivalent circuit. So here from here, IN should be equal to ETH by ZTH. Okay, and Zn, this Zn is equal to ZTH. And here across this particular load resistance we have labeled as in current I1. So if you could prove that I is equal to I dash, then the Norton's theorem is proved. So for that, what we did, what is the current through this particular Thevenin's equivalent? I is equal to this Zn and Zl are in series with each other. So I is equal to V by R is nothing but I is equal to ETH divided by ZTH plus ZL. Okay, so this is how it have come. We have labeled it as an equation number 3. Similarly, the current flowing through the load in a Norton circuit. Now, this is a Norton equivalent of this particular Thevenin equivalent, isn't it? So, no. Oh, sorry. This is. So here, ITH, how the ITH should be calculated? ITH should be equal to what? These two are in parallel. So ITH will be equal to, by using the current division law, I dash, sorry, this is an I dash. So by using the current division law, I dash is equal to ZTH by ZTH plus ZL into IN. This is according to the current division law. I'm once again repeating. I dash is the current which is flowing through the load resistance ZL should be equal to ZTH by ZTH plus ZL into IN. Okay, or we can say that this mathematically ZTH by ZTH plus ZL into, instead of IN is nothing but what? ETH by ZTH. From here you can see that IN is equal to ETH by ZTH. So if you substitute that and if you cancel ZTH and ZTH from numerator and denominator, I dash is nothing but ETH by ZTH plus ZL. So if you compare equation number 3 and 4, you can say that the Norton's theorem is proved. Let's have an example of the Norton's theorem for a linear circuit. So this is a source transformation step 1. This is 25 volt, 5 ohm, 20 ohm current source of the value of 3 amps. This is 4 ohm. These are the two terminals. And now the 25 voltage source is converted to a 5 amp current source. In this manner we can convert it. Okay. Then the step 2 is combination of parallel source and the parallel resistor. So we can have the 8 amp. This is 4 ohm resistor. You can see here. This is 4 ohm resistor. Okay. And the terminal A and B. The third step is source transformation. Combined serial resistance to produce the Thevenin's equivalent circuit. Now we have converted that particular into a Thevenin's equivalent, saying that ETH is 32 volts and ZTH is 8 amps. So this has become now simple to form. The same thing, this can be converted into a Norton's with a single current source. Current is IN is nothing but ETH by ZTH. So it comes like 32 by 8, it comes like 4. So you can see here 4, and this is ZTH. Now we will be finding out the current across this particular AB. Got it? So this is how we can find out as in Norton's equivalent circuit. The next is called maximum power transfer theorem. The maximum power transfer theorem states that to obtain maximum external power from a source with a finite internal resistance, the resistance of the load must be equal to the resistance of the source as viewed from the output terminals. So we just go to the next one. I'll just explain here. Maximum power transfer happens when the load resistance RL is equal to the Thevenin's equivalent resistance RTH or ZTH. Then only we can say that the maximum power is transferred. So to find the maximum power delivered to RL, the power max we will get it as an VTH square into RL divided by 2RL whole square, or we can say that the maximum power equation, it comes like VTH square divided by 4RL. Let's understand once again the statement for the maximum power, and we will prove the value of maximum power should be as V square by 4RL. So the statement is, it states that the maximum power from a source can be transferred when load resistance RL is made equal to the internal resistance of the source. Now you can see that this is the voltage, this is the internal resistance, and this we have given in load resistance. These are the 2 points. So we can say that the V open end voltage, R is internal resistance of the voltage source, and RL is the load resistance. Got it? And this is nothing but this, we can say that this is a practical voltage source. So what is the I from this particular circuit? The current through load resistance is given by IL should be equal to what? V by R plus small r plus RL. So the current through this particular load resistance should be equal to V by R. So V by R plus RL, because these two are in series with each other. We can, so how the power is defined? Power is nothing but the product of voltage and current. So P, because we are all talking about the load power, so load power should be equal to what? V into I, or I just substituted the value of V is equal to IR. So this can be written as I square R or I square L into RL. But what is IL? Just substitute PL is equal to, so you will get it as in V square by R plus RL whole square into RL. So to get maximum power transfer, we will differentiate equation with respect to RL. So differentiating equation 1 with respect to RL. So this comes like dPL by dRL should be equal to d by dRL of V square into RL divided by R plus RL whole square. Okay, this is how we get it. So for the maximum power transfer, that if you differentiate with respect to load resistance, so dPL by dRL is equal to 0. That is, the remaining factor is d by dRL into V square into RL by R plus RL whole square is equal to 0. Differentiate this, just take it V square as an outside because it is constant. So differentiating, we'll get it as an R plus RL whole square into d by dRL of RL minus RL into d by dRL of R plus RL whole square divided by R plus RL to the power of 4. So after doing all the mathematical things, I'll just summarize this. We'll get it as in small r plus capital RL into small r minus capital RL is equal to 0. Or from here we can say that R square is equal to RL square, or we can say that RL is equal to R. It means the load resistance is equal to internal resistance of the voltage source. So this is a condition of maximum power transfer. So substituting small r is equal to, if you see here, here this we got it as an RL is equal to R. So this is a condition of the maximum power transfer. So substitute small r is equal to RL in equation of PL. Equation number 1, we can say that in this particular equation. So what we will get it? We will get it as in PL is equal to V square into R divided by 4R square. Or we can say that PL, the load power, is equal to the maximum power is equal to V square by 4R. Or R is, as we said, that R is nothing but a load resistance. So we can say that P max, maximum power, is equal to V square by 4RL. It means we can say that the theorem is true. The last we have is reciprocity theorem. In any linear network, if a source of EMF E located in one mesh produces a current I in the second mesh, then the same EMF acting in the second mesh would produce the same current I in the first mesh. Okay, it means, once again I'm repeating, if you see this particular circuit diagram, in any linear network, if a source of EMF E, this is an EMF E located in one mesh, produces a I in second mesh, it means, as we have considered an EMF E in first mesh, which is producing a value of I2 value in second mesh, then the same EMF acting in the the same EMF acting in the second mesh. Suppose for the second time what I did is, this EMF is connected into second mesh, and because this EMF, the same EMF is connected in second mesh, which is producing a current value of I1 dash in first mesh. So according to reciprocity theorem, this I2 is equal to I1 dash. It means when in a linear network, when a EMF E produces a current in second mesh, and it produces the same current when it is replaced in a into a second mesh. So we can repeat it saying that in a linear network, if a source of EMF E located in one mesh produces a current I in the second mesh, then the same EMF acting in the second mesh produces the same current I in the first mesh. So this, if it is the I value, so this is also should be a value of I if the same EMF is replaced in second mesh. So now according to this circuit, we say that this is an I2 which is flowing in the second mesh, and here I1 dash, it means I2 should be equal to I1 dash, then we can say that the theorem is true. So we have considered this, an EMF E is connected in first mesh, I1 and I2 are the currents in the two meshes. Okay, so applying Kirchhoff's voltage law, directly I am saying here, so this E should be coming like Z1 plus Z2 into I1 minus Z3 into I2, and second mesh 0 is equal to minus Z3 I1 plus Z2 plus Z3 into I2, because both the directions are in clockwise, there will be a minus. Solving these two equations, we will get as an I2, because we are bothered to find out the value of I2, not I1. Here also, we will not find out the value of I2 dash, we will find out the I1 dash, and we will equate this equation and this equation, and we will see whether it is equal to each other. So solving these two equations, I2 we will get it as an minus EZ2 divided by Z1 Z2 plus Z2 Z3 plus Z3 Z1. Okay, now let the source of EMF is changed to second mesh as shown in figure B. Now the same EMF we have connected here into the second mesh. So what will happen? Again, applying the Kirchhoff's voltage law for first mesh and second mesh. So for the first mesh, because there is no source, so 0 will be equal to minus Z3 I1 dash plus Z1 plus Z3 into I1 dash. Second equation is E is equal to Z2 plus Z3 into I2 dash plus Z3 into I1 dash. So solving these two, by finding out the value of I1 here, because we are bothered to find out the value of I1, so this comes like I1 dash is equal to E into Z3 by Z1 Z2 plus Z2 Z3 plus Z3 Z1. So now if you equate equation number 3 and 6, so this is an I2. So we can clearly see that I2 is equal to I1 dash. Equation 3 and 6 have the same values. Okay, so we can say that the reciprocity theorem is true. These are the few applications of the network theorem. Network theorems are useful in simplifying analysis of some circuits, but the most useful aspect of network theorem is the insight it provides into the properties of behavior of circuits. Network theorem also help in visualizing the response of complex network. The superposition theorem finds use in the study of alternating current circuits and semiconductor circuit like amplifier, where sometimes AC is often mixed with DC. We can also say that it is a pulsating current, because if the output DC have a mixture of an AC nature also, then that can be called as a superimposed or pulsating current. So these are the few applications for the network theorem. So with this, we have finished up all the networks, superposition theorem, Thevenin's theorem, Norton's theorem, maximum power transfer theorem, reciprocity theorem, with a few respective examples. So thank you once again for listening patiently. Thank you one and all.